Hey everybody. I don't think I've ever been introduced as an incredible man before. It's slightly raising the bar, and I hope not to disappoint. I just wanted to kick off by saying thanks to the CogX team for inviting me. This is an amazing conference, and I just wanted to say how impressed I've been, and it's great to be here. Also, I'd like to thank our colleagues at Intel who invited us to come and have helped by creating a stand for us, which hopefully you'll get a chance to go and see. And of course, you guys, I realize this is the slot before lunch, and I'm probably in the last speaker in between you and having a sandwich, so thanks for sticking around. My name's James Parr. I'm the director of the NASA Frontier Development Lab, and now the FTL Europe with the European Space Agency, ESA. I'm actually a NASA contractor, so I don't speak for NASA. I'm not a NASA civil servant. However, about 4 years ago, I pitched the idea to NASA headquarters that they needed to be working with the private sector in commercial and deep learning. Back then, we didn't say AI, we said machine learning, deep learning, but now, of course, we're allowed to say AI. It's sort of legitimate. But we pitched the idea of a public-private research partnership between NASA and really the leaders in commercial AI and private space. So what we've been able to put together over the last 4 years is this amazing partnership. We have Google, who are hopefully here, our friends from Google, IBM, NVIDIA, CogX Systems, and from the private space community, we have Space Resources Luxembourg, who you may know are really leaders in space exploration for mining, the X Prize team, Lockheed Martin, and ESA as well. And what's been nice about the work of FDL is we've really been able to work on problems that matter for the good of humankind. So planetary defense, space weather, looking for exoplanets, and lastly, space resources, which we've been working with our friends from Intel on, and really this is going to be the thrust of this talk today. So 50 years ago, well, actually 49, we went to the moon for the first time. It's amazing to think that's nearly half a century. And when people talk about spin-offs from the space program, people go, well, we have Velcro and we have Tang. And I always get slightly dispirited by this because I'd like to argue that without the space program, we wouldn't be sitting here. In fact, well, perhaps you would, but the computers we'd be talking about be way bigger. They wouldn't be very reliable, and they certainly couldn't see. Because NASA's enabled this. Really, that's the contribution that NASA's made. Radical miniaturization, so this is the Apollo guidance computer, not much bigger than a laptop, and you can see NASA had the idea of gold plating before Apple did. And pretty amazing bit of kit, at least 10 to 15 years ahead of its time, 64K and a clock speed of 0.043 megahertz, which obviously these days, compared to my Apple Mac, 16 gigabytes and clock speed of 2.7 gigahertz, and a little simple, always fun to do the comparison, 63,000 times faster. I think it's about 1,200 times a year that the speeds improved. But I think what NASA did was very significant, and it was the first time that really a computer had been miniaturized to that level. Before that, they were room-sized, and the microprocessor was a big part of that. But it's not just the microprocessor story. Error-resistant code. So this is Margaret Hamilton, who I hope you all know, because she's really a marvelous contributor. And her brief was to be failure-proof, 186,000 miles from home. And if you know the story of Apollo 11, of course, her error-resistant code, enabled that mission to be successful. And really, she's credited with the foundation of ultra-reliable software design. And so the combination of making computers reliable and miniaturizing, and this really gave birth to the PC as we know it. And then lastly, allowing machines to see. This is the CMOS active pixel sensor, which was developed by JPL and has been used on 150 space missions, and of course, really the foundation of modern AI. So, I think NASA has been intimately connected with the growth of computing and vice versa. And really, it's amazing that AI has emerged at the same time as this sort of fantastic explosion of entrepreneurship. And of course, hopefully, the activities of SpaceX and Blue Origin and Richard Branson's Virgin Galactic and Paul Allen's Vulcan Ventures. And really what they're doing is radically reducing the cost to getting to orbit. And this is the hard bit, because once you're on orbit, once you're going at 17,500 kilometers an hour, then really you can start going wherever you want and start doing the cool stuff. And so this is happening, and it's happening as we speak. And I think the future's looking very exciting. So we're going back to the moon for good, and this is an artist's impression. Again, it's not a NASA, I'm not revealing a NASA secret. This is just a message that we're going back to the moon this time for good. And so to do that, we really need to think about what a permanent settlement means. And really the first thing we need to do is find water. Water is obviously vital for human life. This is a speculation of where the water could be, so it's a depth map. But it's really the idea is that there is water at the poles, but really we don't know that for sure unless we go there. And this image is approximately the size of Switzerland, you could say. So you can see, we're getting this concept that there may be water there, but until we send rovers and landers to go there, we don't really know. And to do that, we're going to need artificial intelligence. It's a key enabling keystone to do that. So water, as I've mentioned, crucial for human life, for astronauts. Also can be split to make oxygen and hydrogen, makes a pretty good rocket fuel. And actually a lot of the new startups are thinking about steam as a potential motive force, and radiation shielding. So this work is speculative, but it may be that water can be used for shielding. And of course, ESA and NASA are both planning permanent settlements. This is a rendering from ESA, imagining what a base could be like in the next 10 to 15 years or so. So we need to find water, but we need AI as well to build these things and to do the work of actually having a permanent presence on the lunar surface. So obviously AI is crucial for robotics, but also cooperative robots that know how to work together, change detection, science. There's a full panoply of applications for AI, which a room full of AI experts you can imagine. So the question we asked with Intel was, what could we do? What's a way of solving this water problem? And they were very useful, very helpful in this. And we started working on this problem of automatic detection of craters to assist navigation systems in locating water. So it's a bit of a tricky one. So as I said, this is an image of the south pole of the moon. And this is where it's so cold that it's likely that volatiles such as water will be found. And the reasons why we believe that water will be there is they're permanently shadowed. So essentially, because of the incidence angle of the sun, these craters are always in shadow, and so the sun's never really boiled off the water that was delivered millennia ago by comets and other mechanisms. So because these regions are very cold, this is why we believe that the water will be there. But producing maps for our rovers and our landers is a very time-consuming task. So it's a bit like imagining, I just showed you this area here, which is the size of Switzerland, and finding a small rover in that region. We need to go to that next level of resolution with our map making. And it's a big problem. And so I tried to, for this talk, sort of quantify that, just to give you an idea. And you'll see there's a typo here. The moon is not 37.9 square kilometers, it's actually 37.9 million, so apologies for that. Just in case you thought it was a conspiracy theory. But the moon essentially is a large place. It's the same area as the Asian continent. So we're talking about finding, or finding I guess as I said, a small vehicle in the middle of Russia. That's the kind of scale we're talking about. And we've mapped it we've photographed it very accurately with the Lunar Reconnaissance Orbiter at 50 centimeters a pixel. And again, sorry to disappoint anyone who's got a YouTube conspiracy channel. This is an image from LRO of Apollo 17. This is the landing spot. So if you are a disbeliever that we went to the moon, it's pretty hard to argue with this in 18 different hyperspectral channels. But this is the imagery that Lunar Reconnaissance Orbiter has been giving. But what we want to do essentially is take all of those images and stick them together. And it's a bit like having a billion-piece puzzle with no box. But the added complexity is we don't really know what's on each puzzle bit. And this is why we need AI to do this work. And so why it's difficult, registration issues. So you can see here, putting these images together, there are little artifacts and registration challenges. Just because of the way that this data is captured, there are difference in contrast and shading and varying illumination. So as the sun changes position, obviously it changes the shape of the image, and this makes it very difficult. And just on a normal dev box, just to give you an idea of the size of the challenge, it's about 1,141 years for one human at 20 minutes an image. So really, we need to use AI to speed this up. And essentially what we're doing is we're getting AI to start to understand the edge features of craters, so essentially look at each image and see what's on it, identify the craters, and then that gives us an understanding of that image that can be stitched together autonomously. So NASA FDL, the team worked with Intel to do this. And we worked with a single-shot detector to train an algorithm to do this work. And just again, so if you know about this stuff, you'll know that we use human beings to identify the craters, which is the green boxes, the ground truth, and then the model can replicate that and it shows the model is working. And then once we have the model, we can scale that across the whole lunar surface. And in terms of the results, this is where we got to. Approximately 100 times speed up compared to human experts, and 98.4 agreement with the AI compared to what experts can do. So that's pretty good. But of course, just on that sort of normal dev box, it's still taking a while. And we want to do it instantaneously. And so I think what we'll do is we'll get it onto a big accelerated AI Intel platform, but we need to improve the algorithm as well. And this is really where you come in. And we've been thinking about how to better train the AI to improve the speed and also reduce the errors. This 1.5% error rate, we want to get to 99.999. So to do that, we need citizens. And so again, with the help of Intel, we built this game called Lunar Rush, which is available to play at the stand over there. And we really invite you to come and have a go and play the game, but also in the background help with returning to the moon. And here is just a few screen grabs of it. It's on the URL lunarrush.ai. And essentially the idea is to produce an algorithm that can be used by NASA, but also all of the other organizations that are on their way to the moon, which I mentioned at the beginning of the talk. So it's getting exciting. As I mentioned, there's a new, if you like, family of rovers which are about to head up to the moon, part of the X Prize program. And you can go and see those stories. They're actually really well documented on the X Prize website. And they're all happening in the next 24 months. So there's going to be this incredible sort of surge of interest in the moon because finally private organizations are going back after 50 years. So this year, we're obviously thrilled with the results and we want to do more. And so we're partnering with Space Resources Luxembourg, Intel, and XPRIZE to push it. And the first challenge is to do with landing. And one of the problems with, one of the good things about human beings is when they're in a lander, they can look out the window and they can see where they are by looking at landforms. There's no GPS on the moon, so you really need to have somebody with a map and a pair of eyes to figure out where you are exactly. But of course, rovers don't have GPS, so we want to be able to train an AI to do the work that a human being would do naturally and essentially do constant updating of its location as it traverses along the lunar surface. So that's one problem we're going to look at. And then the second problem is this vision of going to the craters to really start to do mining and remove that water, and we're going to need to have rovers that cooperate. So the second plan is to use AI to create cooperative robotics. That's the vision. And of course, amazing potential terrestrial applications for cooperative robotics as well. Closing thoughts. So I think we've seen that one of the challenges with doing innovation with AI always starts with the data. And sometimes, like in our scenario, we don't have good data, so we've chosen to use games and the crowd and citizen science to create that data resource. And I think this is a powerful new kind of way of thinking about data acquisition. Improving the algorithms by playing games, but also using the crowd to beat the game, to develop algorithms to beat the game. So there's another kind of way that citizens can get involved. And if you are interested in helping, of course, we'd love to hear from you on that. And then, of course, once we've got this technique working, we're not limited to the moon. Pretty much every destination in the solar system is going to need maps of this resolution. And so applying the same tools to Mercury, the asteroids, Mars, and other locations. So really just in closing, this image again from the Lunar Reconnaissance Orbiter, always kind of humbling to see this place. This is our home. We can now go around it in 92 minutes, and we are on this amazing, if you like, I guess dawn of a new age, where we have this tool called artificial intelligence, which some people are calling the new electricity. And I just wanted to finish up by saying thanks for listening, and perhaps looking forward to hearing your ideas on the combination of AI for space travel. And I'd like to wrap by just saying, keep if you're interested, we're online, of course, frontierdevelopmentlab.org, and to thank once again our friends at Intel who have brought us here and been really instrumental in developing the game. And so with that, I'll say thank you, and yeah.